Good morning. Hello. Good morning. Good morning. Good morning. Good morning. Good morning. Hello. 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 Good morning. Christine, good morning.
Good morning.
Yeah, great. Good morning. I want to be sure I'm up. Can you see my screen, please? Or rather, you're seeing the video.
Yes, please.
Oh, great. Hope you don't mind if I share the screen so as to just test what is happening here.
Yeah, please go ahead.
Okay, I can see the host disabled screen sharing. I need to be made a co-host so I can share my screen, please. The host, I think that should be Christine or someone now. the host has to grant me that permission to share, please. Hello? Okay.
to everyone for joining the SP Lagos Petroleum Engineering webinar series today. This promises to be an interesting, informative, technical session. Today's topic is on preferential weld corrosion and integrity of oil and gas facilities. And our speaker is already here with us. So moving forward, I will be your host for this meeting. My name is Oluwabi Aotiko, and I'm co-programs chair for SP Lagos section. This will be our agenda for today. I'll welcome you, and then I will shortly give a safety moment. And then we'll have our opening remark by our section chairperson, the person of Mrs. Fayama Okoli. I will take the honor of introducing our speaker for today, and then I'll hand it over to our speaker, Dr. Michael Abibite. We'll take question and answer, and vote of thanks and announcements. For our safety, let's ensure that we're aware of our surroundings. This is our webinar, and so we're connecting online. And there's tendency that we probably have some headsets over our head, or we have large amount of noise coming from the computer, and we're not paying attention to our surroundings. So let's ensure that we're looking at our surroundings and ensure we know what's going on around us. If you're driving, also make sure that you understand what's going on around you. And you want to put your phone on hands-free if you're doing this while driving, and ensure you're not distracted at all. Avoid eating while you're talking to avoid getting choked. And don't say because an accident has not happened, it cannot happen to you. Carefulness costs nothing, but our carelessness may be very costly. So let's ensure that we're careful, we are aware, and we continue to remain safe. I'll run us through a virtual meeting etiquette. Ensure you have your microphone muted when you're not speaking. Stay muted unless you are asked to unmute your microphone and speak. You can ask questions two ways. You can either use the chat box to post your questions, or you use the raise your hand button and wait for your turn to ask a question. When you raise your hand, please do not unmute your microphone immediately unless you've been asked to do so that you do not disrupt the flow of the meeting. We'll, as much as possible, ask you not to turn your video on for now. We will still request for you to turn your video on when we want to take a general picture. But for now, please keep your video off so it doesn't distract. Let's minimize distractions as much as possible. Video meetings have enough background noise, so let's not to it. And let's join from a place where we can all focus. In this meeting, let's as much as possible try to be patient. If someone does not respond to your question immediately, give time before you prompt again. So just use the chat box to call my attention to your questions or anything you want, or your contribution as good. With that, I'll then hand over to our section chairperson, Mrs. Fayama Okoli, to take the opening remarks. Over to you, Fayama.
Thank you, B. Okay. So I would like to say a very big welcome to all our members and our lecturer, distinguished lecturer this morning. We are delighted to have you part of us today at SP Lagos section. I know that the numbers are a bit few now, but as is typical, it will continue to grow. And with that, we expect that more people will join in as we progress along the course of the meeting. At some point in the session, we would also ask for everyone who can to put on their cameras so that we take a screenshot of everyone in the call. So I kindly request that you oblige us when the call comes, so that we have a capture of yourself and others who have joined this meeting this morning. So the Society of Petroleum Engineers, SPE Lagos Section 61, is an arm of SPE International. Some of you may already know, but for the benefit of those who do not know yet, SPE is a non-government, a non-profit organization, and it's a global organization with more than 124,000 members all across 134 countries and counting. SPE as an organization's mission includes collecting technical information, disseminating that information, exchanging around exploration, oil and gas development, production, and all that kind of focused knowledge sharing within the industry. You might wonder why I am taking time to describe the foundation of what SPE is all about. As a section here in Lagos, we are also very keen on ensuring that we operate by the tenets of the society, meaning that we believe in the dissemination of technical knowledge. It is with this vision that we have put together the Petroleum Engineering webinar series. And the intention, the hope here is to draw the industry back to the foundation, the very foundation of oil and gas. I know that today there's a lot of discussions around energy transition, energy mix, renewable energy, clean energy, and all the likes. But we want to, while we are having that conversation, because it is the drivers of the industry decisions today, we also do not want to forget the backbone of the industry that has brought us to this point, which is the technical knowledge around the oil and gas industry. So it is with this reason that we have put together 4 of these petroleum engineering webinar series. This is the first of the series. So if you have joined us today, you are really welcome. I crave your indulgence to register as well for the other 4 series. You have a lot to benefit from this in-depth technical sessions. And as professionals, we want to grow in our careers. We want to grow in our knowledge areas. We want to grow in our areas of expertise. There is no better way to do that, achieve that, by spending these 45 minutes to get new knowledge without having to leave your desk. So with that, I say a big welcome to everyone in the call today. I say a big welcome to our lecturer for the day. And I implore us to have a very healthy, very productive session and deliberations this morning. Thank you. You're welcome. So be over to you.
Thank you very much, Section Chair, for that great opening remark. I now go ahead to introduce our speaker for today. Dr. Michael Adedokun Adebite is currently the Director of Offshore Technology and Energy Center at the Petroleum Training Institute, Nigeria. His interest includes performance of welding joints. He has authored and co-authored over 30 papers, supervised graduate theses, and conducted notable commission projects. Dr. Michael is a certified welding inspector and holds a BSc in metallurgical engineering, MSc in welding, MSc in offshore and ocean technology, and PhD in corrosion engineering. He is a fellow of the Nigerian Society of Engineers and life member of the American Society for Non-Destructive Testing, among others. He chaired the Society of Petroleum Engineers Section 104, that's the Warri section, in 2009-2010, and received many distinguished awards, including the 2019 SPE Project Construction and Facilities African Region Award. Ladies and gentlemen, it is my honor to welcome Dr. Michael Adebite to present to us this morning. So with an round of applause, let's welcome Dr. Michael Adebite for his presentation.
Thank you very much. Thank you very much. It's a pleasure being on this call, and it's I don't take it for granted. Thank you very much. I'm sure you can see my slide, please.
Yes, we can see your slide.
Oh, great. So again, it's a pleasure being on this call. Thank you very much for having me, the session chair, and all the session, legal session board members. I say a very big thank you to you for choosing to have me on this webinar series. It's also my pleasure to share this knowledge with you. It's that which the SPE during the course of this year taken on to be the Distinguished Lecture Series. So thank you again for having me. The Distinguished Lecture, you will recall that it is primarily funded by the SPE Foundation through member donations and a contribution from offshore Europe. So the society, that the SPE, is grateful to all the companies that allow their professionals to serve as lecturers. And the program is also supported by the IAME, that's another arm of the SPE. And grateful to SPE again and Petroleum Training Institute for granting me this honor and privilege. The topic we'll be sharing together with is preferential weld corrosion and integrity of oil and gas facilities. We know very well that oil and gas facilities are very, very key in achieving our objectives of producing hydrocarbons, bringing them from the reservoir to the surface, to storage facilities, processing, transporting, storing, and of course, distribution and supply down to utilization. So it's very, very key. Facilities are very, very key. And a lot of facilities are being used, very assorted materials, from concrete to metals to plastics to glass and other materials are being used. So facilities are very, very important. And a key aspect of it is the metal, and that would be our focus. And all these assets must be managed effectively and efficiently so that the production of our hydrocarbons is not only economic, but also safe and very, very cost effective. So the outline of this presentation will be the occurrence. We'll take a look at the occurrence. What is preferential weld corrosion? What is it all about? Is it a big issue? What are the challenges, especially in the oil industry? How do we come about this preferential weld corrosion? And that will take us to looking at the basic chemistry or basic electrochemistry or basic corrosion that most of us are familiar with, especially once you're science. And even those that are arts or non-science oriented, corrosion is a natural phenomenon. And we'll be seeing this as we go on. We'll be considering whether there's something beneficial at all from corrosion too. And then we'll be looking at corrosion associated with flow. Anytime we have movement of a continuum, is there any corrosion that could be associated and what are the likely issues and challenges. And then the development of submerged jet impingement, issues around that, how this target is developed and then being deployed and assessed. And we look at some lessons learned, and then we run with some of the conclusions so as to implement in managing our facilities better. Well, corrosion, again, is a natural phenomenon, and simply put, is a reaction or interaction between a material and its environment. Material now, it could be textile, it could be glass, it could be concrete, it could be metal, it could be plastic, composites, and other forms of materials. So when we have an interaction, basically electrochemical reaction, that's what we refer to as corrosion. In this corrosion process, what simply happens is that a material will want to go back to its natural form. Simply put again, dust are thou, and dust shall thou return. And what are the possible consequences of this natural phenomenon? Materials properties are degraded, especially desirable properties, could lead to premature failure, excessive maintenance, repair, and replacement, long-term production, especially when it is not well managed. There could be product contamination. We can have ingress of the environment into our product, and that contaminates the container or our product. We can also have product loss, and the accident could result from this. Product loss, again, could result into environmental pollution, both soil, water, and air, and other concomitant effects, such as secondary effects, such as fire and life. And of course, the whole infrastructure being lost. And that will impact on production and all the production economies. It's not all negative about corrosion. There are some good things about corrosion. And three basic things or major that are very, very positive that we take advantage of electrolysis. Electrolysis, in everyday language, we're talking of coating of a metal with another metal. We take advantage of corrosion to do this, and with that, we can protect a material that can easily interact electrochemically with environment. So some of the products, even domestic products, roofing sheets. We talk of zinc-coated or anodized aluminum roofing sheets. This, again, take advantage of electrolysis. Battery, you can imagine what life would be like without batteries. Batteries and power storage systems. Batteries in various forms, either wet or dry. Wristwatch batteries, our handset batteries, our laptop batteries, the batteries, Berek and others that we make use of to power the clock, wall clock, and perhaps vehicles. So all these battery and power storage systems take advantage or exploit corrosion. They depend on corrosion phenomenon to function. Also, in terms of technology, machining, we are familiar with machining, mechanical machining that involves mechanical removal of material from the surface in order to shape a metal. We can not shape high precision components using the conventional or even the high precision CNC machines. So we lean on electrochemical machining and milling equipment in order to machine systems with high precision. tolerance limit very, very low. So we take advantage of corrosion phenomenon to produce this. Anytime two metals or two pieces of metals are welded together, making use of fusion weld, that is, whenever we fuse them together, we bring them to liquid state and allow the liquid metal to mix together, and then on withdrawal of each source, this liquid metal being mixed together, and now we cool down and then solidify. There are some things that attend to that process whenever we join. Minimally, we have three distinct areas whenever we weld, and very, very important. We can see the region of weld metal, and then an adjoining region referred to as heat affected zone, and then the parent metal. The parent metal is the metal far away being welded, but far away from excessive effect of heat that is being experienced or that accompanies the welding operation. And when such solidifies, we see that, well, the parent metal retains its structure, its phase phenomenon, morphology, whereas the heat affected zone, yes, the same composition as the parent metal, but because of the intensity of the heat experienced in that region, there is crystallization, there are phase changes depending on the nature of our component. There are changes in phases, in the phase compared with that of the parent metal, and these will also be associated with energy level. Of course, the high distortion associated with the weld metal, that is the metal that solidified, highly distorted nature, we can also see. So there are three distinct structures, and this again depends on the number of runs, the number of weld bits that are being laid. But minimally, anytime we weld, we have three distinct regions, areas, possessing different energies, and that's the heat affected, the weld metal, the heat affected zone, the weld metal, and then the parent metal. So these are characterized. So in essence, the weldment is the region, the entire region around the weld. The weldment is characterized by chemical composition, that's variation in chemical composition, that's the weld metal. The weld metal, the composition is different. Then the metallurgical phases being present also associated not only with the weld metal now, but also and much more the heat affected zone. And of course, the residual stresses associated with non-uniform cooling. You appreciate that the cooling is so sudden. Heating up a metal before to welding state, you're talking of a sudden increase in temperature from whatever the ambient temperature. Even when we preheat, you can imagine even preheating to about 300 or 400 degrees, and now during welding, the temperature is escalated to beyond 2,000 degrees centigrade. That's shock, a shock, metal shock or thermal shock rather. So such thermal shock has with it residual stress associated even in the cooling, regardless of the amount of post-weld heat treatment or the amount of cooling that we can control, the amount of controlled cooling that we can achieve, there will be a measure or a number of residual stresses associated with the weldment. So we can see here typical morphology being shown here. So that's we move on to the next slide. Excuse me, please. Okay, so the next slide, we are looking at a typical post-weld corrosion incident. Here is an incident. When we say preferential weld corrosion, we are considering selective attack of the weld metal or selective attack of the heat affected zone, or perhaps both. So it could be either the weld metal and or the heat affected zone being selectively corroding, going into solution rather than the parent metal or the base metal. So when they are joining base metal, is more noble or will not corrode as fast as the weld metal or as fast as the heat affected zone, or the two of them combined, then we have what we refer to as preferential weld corrosion. So it's commonly encountered in oil facilities, and the consequence, of course, is that of premature failure, economic losses, downtown in the terms of production, and of course, environmental pollution. And a typical example here, we can see the joining metal, the heat affected zone going into solution rather than the parent metal. So in this case, we have the weld metal being selectively corroding in this case. So it's selectively corroding compared with the heat affected zone and that of the parent metal. And this happened within 15 months being in service. We can see that this led to a failure around the reducer and then a shutdown. So a facility that is expected to serve for 20, 25, 30 years within less than 2 years failing, that is not acceptable. So what could be responsible? Can we mitigate it? Can we reduce it? Can we avoid it? Perhaps much more is, can we predict it? Another typical example is carbon steel flow line section having a pinhole leaks. This happened 30 months in service. 30 months, that's 2.5 years in the Gulf of Mexico. And this is typical of what happens around the globe. So they need to roll up sleeves and be able to predict, to see this, and then be able to mitigate if we cannot prevent, to be able to mitigate. So what are the major factors that can influence preferential weld corrosion? Electrochemical characteristics of the weldment, that's the vicinity. What is the electrochemical nature of the vicinity of weld? We can see that typically composition, phases, and energy associated with each region varies. So there is variation in energy associated with each region or regions across our weld, and that's very, very important. So we need to be mindful of the fluid too, or the environment, the flow pattern, especially in pipelines, flow patterns, be it gas or liquid, any form of liquid at all, or fluid rather. We need to be mindful of this. Even some may be combined with solid particles, where we can also have erosion. So all this, we have to roll up our sleeves and take a closer look. How about inhibitors? Yes, before now, inhibitor is being deployed. Inhibitor being deployed, yes, but it's also noticed that inhibitors are ineffective in some instances, especially where we have a flow. Inhibitors have, they are not effective. Another typical measure being taken in combating corrosion or managing corrosion generally is that of corrosion allowance. Corrosion allowance typically makes room for corrosion over a period of time. Unfortunately, we can see, as we have seen in this particular case, is a localized corrosion. General corrosion is what corrosion allowance is concerned about. Whenever we are making use of corrosion allowance, then the assumption is that corrosion that is prevailing is general or uniform corrosion. Unfortunately, preferential corrosion is not uniform. Temperature of our system is also very, very important, and that of the corrosion product too. So all this, so these again are typical examples. And what are some of the challenges? Again, the mechanism is a challenge. How does preferential weld corrosion occur? We need to know. Location of attack. Can we determine which location, whether it's the weld metal or the heat affected zone, that will be attacked? Or can we predict that, or perhaps even prefer that it should be the parent metal? How about the efficiency of the chemical inhibitors being deployed? I've mentioned this, and unfortunately, it's a common knowledge now that inhibitors are inconsistent and they are not effective in some instances, especially instances wherein there is flow. And what are some of the susceptible conditions that could lead to this challenge? And how exactly can we evaluate in a flow regime, or where we have flow in a flowing system, in a dynamic system rather, how can we evaluate the shear stress on the wall of our containment, or the wall of our material, or the wall of our pipe, the wall of our storage tank? How can we assess the shear stress so that we can know the rate at which, or the conditions that could lead to removal of protective layers? And then we'll be able to mitigate this preferential weld corrosion. It's a big challenge, but there's no challenge without a solution. And that essentially is what this discourse is all about. It's a common knowledge that whenever we have two different metals, we have what is referred to as galvanic corrosion. When two different metals are joined together, present together in the same electrolyte, in the same system, and they are electrically connected, it's that's the condition for galvanic corrosion to occur. And exactly what do we have whenever we have metal being welded? Is it typical, or do we have these conditions being satisfied whenever we weld? Well, we'll be able to answer as we go on. And let's look at some of these conditions again. The three conditions, again, is that at least two materials, different materials, will be present in the same electrolyte, should be joined together, and also being in the same electrolyte. So of these three systems, or these three systems that we have here, which will you say that galvanic corrosion will occur in? Which meets the three conditions different metals being electrically connected and in the same electrolyte. Which of these three? I wish we can have a response, please. You may wish to unmute and then, just by voice, share with us the first, that's 1, 2, or 3, please. Yes, please. Will it be in the first or in the second or the third place? Yes.
So,
Can we
so
have
they're already dropping the comments in the chat box.
Oh, great. Great.
Yeah, so I've seen 2 people said 3.
3. Oh, fine. That's 100%. Thank you very much. Yeah, in the third system, very well. That the third system meets the requisites. 2 different metals electrically connected in the same electrolyte. And you will agree with me that that is exactly what we have whenever we weld. The metals being joined together, they are electrically connected in the same electrolyte, and of course, being different. The 3 regions we have seen in a typical weld, the 3 regions, that at least there are 3 regions that are different, and energy they possess also differs. So that difference is enough to trigger what we refer to as corrosion, because there will always be flow of thermal energy from region of high temperature to the region of low temperature. The same thing in a conducive environment, there will be a flow of energy from one region to another. And that's essentially what happens when corrosion occurs. Metals having higher potentials will tend to now assume a lower potential. That's losing some of the energy and assuming a more comfortable low energy state. That's essentially what happens whenever corrosion occurs. So a more active metal, that's the anode, reaches higher potential and corrodes faster. And the more noble one is the cathode, and corrodes slower or at a lesser rate, is being protected, galvanically protected by the anode. So the cathode enjoys a measure of protection, and that is what happens when we have preferential weld corrosion. So whenever we have preferential corrosion, it means that the parent metal is enjoying considerable protection while the weld metal and or the heat affected zone goes into solution. And that's what we don't want to occur. So we want to reverse that trend. We want to deliberately make the parent metal be the anode, be the one that will have higher potential, or be the one that will go into solution. You will agree with me again that because the cross-section area of the parent metal is more than that of the heat affected zone and the weld metal, then it's better for the parent metal to give more, because it will feel the pinch, the pain, so to say, lesser compared with the heat affected zone or the weld metal. So in a flowing system, there are also some considerations. Whenever we have flow, there are consequences, and these are some of the things we'll be looking at. So there are some methods before now that have been deployed: the recirculating flow loops, the rotating cylinder, rotating cage, and the submerged jet impingement. I just need to step forward a little because of our time. So, and then that's essentially, we'll be looking at this. We want to use this to simulate the turbulence or the flow pattern in a typical pipeline. And the conventional methods, unfortunately, they fall short of what the real situation of field, typical field situation is like. They fall short of that. The one very close to it is the submerged jet impingement, and that is what is being employed in this particular project. In typical work that have been used to study the effect of inhibitors and to study preferential weld corrosion is this work by Martins. Study the work, but because of the limitation of the speed or because of the limitation of the shear stress that could be generated, that could be simulated, this particular method falls short of it. But all is not just negative. A lot of lessons that we can learn from this work. And it is that it demonstrates that indeed inhibitors, chemical inhibitors, are inconsistent. They are not as efficacious as they have been assumed to be. Looking at the graph on the left-hand side, you will see a sinusoidal, a reversal of current of the galvanic current wave. So the current, the blue indicating the parent metal, the heat affected zone is the red, and then the green is the weld metal. So you can see the reversal, the sinusoidal nature. And whenever we are above the 0 level, that is when we have the anode. Any region above the 0 positive current here now is the anode, that is the metal goes into solution, the component that goes into solution. So selecting each of these phases, the weld metal, the heat affected zone, and the parent metal, looking at them separately and joining them when necessary, we see that one there is a reversal. There are times a component behaves in an anodic manner, that is, goes into solution, and there is a time it's protected. And this again is under inhibition. So it means that the inhibitor is inconsistent. And there are some things that will lead to that. We'll be looking at that as we go on, please. So in order to really simulate field conditions wherein we have a shear stress in excess of about 200 newtons per mm squared. What we have typical is less than about 70. That's what the previous tests have indicated. And then we need to get closer to what the flow conditions is like. And in modeling, this a medical, conventional knowledge too, especially to colleagues who are mechanically inclined. Modeling, model, simulate, and typical modeling field situation in the laboratory, and then using an equivalent hydrodynamic factor to evaluate what could be a typical flow condition or shear stress in the field. And this solution or this data is used conventionally, and the same is exploited and being used to evaluate or study typical flow regimes in the field being simulated in the lab. Another tool being used is computational fluid dynamics. Computational fluid dynamics exploits various segments, of a particular system being broken into smaller units and being studied. So flow pattern being studied in a smaller unit is what is being demonstrated here. And that flow pattern, it's typical, or it could be seen that within a radial distance of between 2 and 3, especially around 3, we have a radial distance that is associated with high flow, high shear stress, a turbulence, high turbulence in terms of flow regime, flow patterns. Of course, directly under the jet, let me spotlight that. Directly under the jet, that's under the jet, is a stagnant region. And the same could be noticed in this stagnant region. That's directly under the nozzle. And then a radial distance associated, with twice the radius of the nozzle is where we have high turbulence. And then moving radially outward, we can see the flow pattern, typical flow pattern in terms of low turbulence. And that shows that when we have flow, regions, there are some regions associated with high turbulence and some regions, especially at the elbows, some regions will be stagnant. And then we also have regions with low shear stress. And that's typical, and this is used to study this particular, in this particular study. So nozzle being put together, we have the nozzle, the jet, and then we have the targets being mounted in radial distances. We have laminar stagnant region, the high turbulent transition region, and then the low turbulent region. These are characteristics of the hydrodynamic system under a flow regime. A typical weld is being prepared, and the various segments of the weld being selected and mounted, isolated from one another, but being mounted around the same flow pattern that we have, so as to plant these electrodes or these specimens in these three major regions that have been identified. That is the three hydrodynamic regions that have been identified: the stagnant, the high turbulence, and then the low turbulence. So the same thing is being done here, and then we have the assembly of the various segments, isolated and then being joined electrically via copper wire connection. The test, looking at the corrosion rates, self-corrosion, galvanic, and then looking at the corrosion product features, and then the features of the product, and then what exactly could be the controlling factor. That's the very third test, that the scanning that was done. Let me quickly move faster now because of time. So tests conducted in stagnant system, in a flowing system with 5 meters per second, and that 5 meters per second is typical of a wall shear stress of about 72 newtons per mm squared. And at higher flow rate is typical of, is associated with 250 newtons per meter squared. Whereas the atypical flow field condition, oil field condition, we have a wall shear stress of about 120. So 120. So this particular method affords us to even go beyond typical flow field situation. So the test being conducted, we can also see the reversal of the corrosion current here, the galvanic current. It also establishes that the inhibitor is not consistent. So this in a typical with a typical chemical emitter, and we can see the reversal, current reversal. The current reversal shows one that there is a buildup of protective layer and then a breaking of the same. And when the time we have the breaking of the protective layer, the corrosion rate spikes. And of course, it shows that the emitter is not reliable as we are taught it will be. And plotting, looking at the values and putting them together, we can see here the very first one. Let me also just come up with the first one here. We can see in a no flow situation and uninhibited, that is without inhibitor, we can see a typical corrosion rate. The flow, the heat affected, or rather the weld metal is the green, the heat affected zone is red, and the parent metal is the blue. So without flow, that is in a storage system, we can have what we refer to as preferential weld corrosion. Anytime or rather here, this first one, preferential weld corrosion is only when the corrosion rate of parent metal is less than that of the parent, the heat affected zone, or the weld metal. So here in no flow and uninhibited, we can see that the corrosion rate of the parent metal is higher. So there's no cause for alarm in this instance. That is no preferential weld corrosion. But something of note is that with inhibitor, we can see the corrosion rate. The allowable corrosion rate is 1/4 millimeter per year. That is the usual corrosion allowance. When we say corrosion allowance, is make rules for the fact that corrosion rate could be or maximum 1/4 millimeter in a year, uniform. And we can see the corrosion rate here is crashed of all the components across the entire weldment. It's crashed far below that. And it means that the inhibitor here, in no flow situation, the inhibitor is very, very effective. But how about when there is flow? This is in no flow situation. That is no movement. The inhibitor is very, very effective. And we can also see, yes, there is corrosion, but the rate is minimal, and that of the parent metal is less, is higher rather than that of the heat affected zone and the weld metal. The heat affected zone is the red and the weld metal green. Well, that's not what we have when we have flowing condition. In flow condition, we can see the weld metal is higher in inhibited, and when we even inhibit or run flowing at higher rate, that's 10 meters per second, that's in a typical field situation, higher than a typical field situation, we can see the pronounced preferential weld corrosion. That is the rate at which the weld metal and the heat affected zone corrode is higher than that of the parent metal. And that's essentially what we have in a flowing condition. So the same result being displayed, and we can see in a flowing situation, in a flowing condition, there is a challenge of preferential weld corrosion. Anytime there is flow, preferential weld corrosion can occur, and that is usually taken for granted that it cannot occur, and that's why we have this challenge, and we can now see that anytime there is flow, we can have this challenge. Well, another typical situation is where when we have aerated system. In aeration, let me just make use of the pointer again, please. In situation wherein we have aeration, that is air ingress perhaps into our system. In a typical practical field situation, perhaps the service fluid is poorly treated, or we have air ingress into our facility, leakage of pumps, leakage of the fitting systems. Then we have air, especially oxygen, into our system. And when the time that occurs, we have a spike in corrosion rate, and we can see that aeration, either uninhibited or even when it's inhibited. We can see even with inhibitor, corrosion is even higher because of admission or admittance or ingress of air into our system. So we have to keep eyes on air with respect to our systems. So we must keep away air. We shouldn't allow that. We're looking at the morphology. We see mud cracks that the surface, the protection or the corrosion product does not offer protection to the underneath layer. And that's what we have here. Because it does not offer protection to the underneath layer, it means corrosion goes on anytime there is flow, regardless of the corrosion product on the surface. The underneath layer is not protected. This is what we have when the air is admitted. That's red, and without air is the blue. So we can see this is a log current density. So we can see order of 3. That's the corrosion rate is increased by a 3rd order, and that's a phenomenon. It also corroborates the results that we've also seen in this particular graph. That is the spike in the corrosion rate compared with when there is no air in the system. What can we do? Lessons learned. In design now that we know, it means that in the design stage, we should not take things for granted because we have learned our lessons now. The entire value chain is susceptible to preferential weld corrosion. And then what can we do? As a predictive tool, we need to across all, it's not good enough selecting the most suitable material. Our concern will be the properties of the welded joint, that is across the joint, because that is the concern now. We are not just using the material as it's being produced, but we will be joining. So that area of joint, that's just like a chain. The weakest link is should be our main concern, our focus. So that is why we need to focus on the materials, and then the fabrication, the installation and commissioning, operations, production parameters, especially, we want to increase production rate. Increasing production rate means that we want to increase the rate of flow. The flow regime, it means that the whatsoever corrosion product that perhaps could be offering partial protection will be easily removed, or any product being formed will be removed, and then a fresh surface is exposed, and then corrosion rate spikes. Also of importance is admittance of air into the system through poorly treated system service fluid, and of course ingress through poor or bad pump systems or any of our valves that we may be using. And of course, it also informs our inspection and maintenance planning. In service, we then need to roll up our sleeves in choice of our inhibitors. So there is need to conduct case-by-case inhibitor characterization for our system, and not only for the system, but also for the flow regime that we have in mind. Very, very critical in order to justify overall production. So we need to choose our flow rate very well, not just fire down, and we need to be more careful now because we have the big picture in mind. Aeration, I've said that, drilling fluid poor treatment of system, and of course, leaking pumps and equipment. And of course, effective monitoring, very, very important. In conclusion, efficiency of our inhibitor in high, the efficiency is high when there is no flow, especially in storage systems. But then when in storage system, how you get the fluid into your storage system matters too. So, but generally in stagnant situation, yeah, inhibitor is reasonably efficient. But when there is flow, as a result of the shear stress exerted on the wall, that efficiency is lost. So a rated system will easily result in to preferential weld corrosion, especially when we have oxygen, and oxygen, we have seen that oxygen, the corrosion process there is under oxygen mass transport control. That's the scanning that was done and the graph being demonstrated. Now we can better manage corrosion, and then it's also been demonstrated that this is a reliable tool to mitigate and to predict preferential weld corrosion. So it is now possible. I want to say thank you again for your kind attention, and we'll be delighted to take on questions, please. Thank you very much again for your attention and for your having me. Thank you. Yes, please. Hello.
Good afternoon, sir. The moderator will join you shortly. The host will join you shortly.
We do have some questions in the chat box, so we might as well start with those ones. Okay, so we have a question from Abu that says, please, what are the known techniques for evaluating and predicting PWC?
The techniques.
Yes.
In terms, well, now, making use of jet impingement. So we can reasonably predict this preferential weld corrosion. The target has to be well prepared, and the field condition has to be carefully simulated. That is, carefully being reproduced even in our test facility. And with that, so this particular is being deployed very well in the industry now, and across various labs and research systems, especially in managing corrosion. So it's typical, and it's a very good tool to predict or to manage the corrosion associated with preferential weld corrosion.
Okay, thank you very much.
Thank you very much, Section Chair, for helping out. Sorry, I lost network for a bit, and then I was no longer co-host, so I couldn't unmute myself.
You're welcome.
All right, so I think there's another question, which is not more of a question, so we'll take that as the last part. I think before we continue on the questions, I just want to give a brief summary of the talk. I think this was an excellent presentation. It was like I was in a PhD master's class learning about the corrosion. And we talked a lot about a lot of things. My book is full of what I had to, things I wrote down. So you talked a lot about how preferential weld corrosion occurs. We talked about the three distinct regions, which was really very important and clear. The region of the weld metal, the parent metal, and then the heat affected zone. And you told us about why the weld area, which is the weld metal area, is very important to recognize because there are changes in the chemical composition and the metallurgical phases also change, and then there is residual stress as occurred in that area of the rod metal. And we went ahead to talk about the factors that influencing weld corrosion and the chemical characteristics of weldment. And we talked about the flow patterns and how flow-induced stress, especially in pipelines, can affect preferential weld corrosion. We also talked about corrosion inhibitor ineffectiveness that you also talked more about later in the presentation. And temperature also being a factor. And then you went ahead to tell us the issues and challenges and that can occur. You talked about the mechanism itself not being well understood and being difficult, and we need to do more work understanding the issues around that. And we don't even know where the location of attack will come from, maybe the rod metal or maybe the heat affected zone. And then we talked about again the corrosion chemical inhibitors, and then the conditions that could lead to us having this corrosion. And then you taught us about galvanic corrosion. I'm saying taught because this was like a class, really, right? You taught us about the galvanic corrosion, how it occurs, the two different metals being electrically connected together, and then being in the same electrolytes and leading to galvanic corrosion. And you then step up further by then introducing the flow accelerated corrosion, which is now more where you spend a lot of time explaining some of the work that's been done around the submerged gas engagement. How moving from the laboratory flow condition to the field flow condition, and bringing in computational fluid dynamics on top of that to simulate the flow accelerated corrosion. And you talked a lot about the experiments, and then for me the thing I'm holding now is the part where you talked about the lessons learned and how we should consider the entire value chain while thinking about the facilities that will produce this oil and gas, from the exploration and production phase down to the refining phase. And you clearly also explained to us that material selection, fabrication is important, installation and commissioning, and these are very important when we want to consider the design of oil and gas facilities. And lastly, you ended, or you also talked about while in service what we need to do, choosing our flow rate effectively, working on better indicator performance, and doing effective monitoring, going to check on this method to be sure that the cathode has not become the anode and the anode has not become the cathode. I'll put it that way. And lastly, you then concluded by giving us tidbits about what we need to understand about the efficiency of inhibitors, while emission even increases, a threat to preferential weld corrosion, and a little bit about corrosion. So this was it was a very, very lovely session. I learned a lot in just an hour, and this shows the value that SP really brings to the table. And I'm sure a lot of people have also had great learning from this talk. So I will then proceed to the next question that we have by Ezina. So Ezina is asking that, can etching and bonding minimize the effects of corrosion or corrosion rate in a facility?
Yeah, no. Etching and bonding will not be able to. They serve different purpose. Etching essentially, well, for electrical conductivity, you appreciate that. But that does not, it can even accelerate, especially the contact, because you now have another galvanic system. Etching, of course, you appreciate is more of copper. And then with the bonding, well, bonding, many a times the component being used non-metallic, but then that it depends on the overall system really, but does not necessarily reduce corrosion of a facility. There are chances of increasing it rather than reducing it. Thank you.
Thank you very much for that excellent answer, sir. I don't know if any other person has questions. You can raise your hand and you will be made a call so that you can ask a question. Is there anybody that wants to ask a question? Please use the raise your hand button and you'll be unmuted to ask your question. Okay, yeah, so we have Engineer Wale Ajao raising up his hand. So you can go ahead and unmute and ask the question.
Yeah, okay. Good day, the teacher and colleagues on this webinar. Well, my question actually was scribbled at the time down. And in cases, I'm a petroleum engineer working as a production technologist. I've not had time to be doing with corrosion inhibition, welded joints, corroded welded joints, etc. in a long while. But I actually remember some offshore incidents and accidents, especially the past one because of the vessel that has been highly corroded and which was not moved for dry dock before the fire incident. In all, I follow Engineer Degbite from the beginning right to the end and really thumping up and jumping up on my seat because a very sound teaching. I mean, unalloyed, in the language everybody will understand, taught as if there is nothing at stake, as if we are chit-chatting. And then I asked, are there other lectures, other topics assigned to him to take? Please add me. Let me have the invite. I love to listen, sir. Thank you.
Thank you very much for the compliment. Thank you.
So Dr. David, I'll be reaching out to you to get your schedule and when you will be speaking on other topics so that we can also share with Engineer Ajao so that other people will be interested.
Yeah. Let me also use this first again to say thank you for the compliments and also to invite all of us on call to please subscribe to the short course. The short course that will be coming up just before NICE 2022. One of the courses that is on the menu is facility management, oil field asset management, and I'll be facilitating that in collaboration with Engineer Emmanuel Okudo. So we'll be facilitating that together. So it will be a delight to welcome all on this call to that short course session too. Thank you.
Yeah, thank you very much for the invitation. Yeah, I guess more communications will come on the short courses. And
yeah,
everyone can see that. So we have another question here in the chat from Abu. So Abu is asking, is there an industry reference one can consult when formulating a corrosion management program or plan?
Yeah, industry, generally there are ISO standards and references. There are also specific industry because again, we can see one have to be mindful of something generic. So whatsoever that is even being specific, one will deliberately have to configure for one's own system. For example, say a beverage industry. You have a Coca-Cola or perhaps Well, even the oil industry, you have, the Shells and the Chevron and the Mobiles. Yes, in the same environment or producing the same industry, but each facility differs, even in the same shell. You can also consider reservoir characteristics. So characteristics of the reservoir, differs. Oil salinity differs from one period to the other, and a lot of all these. So it's usually customized. You have something generic, yes, but it has to be narrowed. It has to be tailor-made for a particular situation. Yeah. So in this case, or to respond again, whatever the situation we have at hand, is it in drilling? If it's drilling, look at the drilling pipe, look at the characteristics of your hose and all the facilities involved, and then one can be able to learn from previous incidences and within the industry, and then use that to transfer the knowledge now to this particular field that perhaps you now have upcoming. Any new field, you can be sure that you also very likely to have new materials. Even if you want to make use of materials you are comfortable with. Comfortable with, in essence, means that you have data, reliable data on that material. Fine. Then you now have to talk of welding parameters. Not just the material, we're not also concerned with the fabrication, the handling, and then other things following, because each of these stages imparts its own signature on that component and the environment. So you have to be mindful of the signature, and then that's what determines the performance in service. All the others is being equal. If you come to inhibitor, you say, oh, this is inhibitor, very reliable, this and that. But if perchance the flow regime differs from what the data that the inhibitor is based on, then you have something else at hand. It could be by any order, or even an ingress of air into the system. All of that being equal, you then have a different system. And this again, so there are, depends on the industry and perhaps something specific, one can take it up one on one. ISO standards are there, the World Corrosion Organization, a lot of data sheets and standards and recommendations or guidelines are also there. And then industry specifics also are also there. And of course, the client will also want to suggest something, or the particular industry may say, in this industry, this is what we are, agreeing, and that's it. Or even the country, depending, there are some fields, is it sour or sweet? Yes, we deal mostly with sweet situations here, but there are still some fields, even in Nigeria, that are sour, sweet fields. So these are things that will change the game, game changers. So, but then there are standards, and all these are available, either on the shop floor, or on the shelf, or perhaps industry specifics. And if there are specifics, we can discuss further on that, please. And it will be my pleasure. Thank you.
Thank you very much. Thank you very much, sir, for that well-explained answer to the question. I think with that, I don't know if we have any more questions. If not, we've come to the end of the presentation, and then I will quickly share my screen to give some announcements and updates that will be coming up. So just to also share that you will be getting the slides shared by Dr. David. So we'll be sending that out to everyone to be able to also learn more from what Dr. David has shared here today. Thank you very much again, Dr. David. So, yeah, I think at this point in time, so that we don't lose so much people, I would request that we'll be able to, unmute shortly so that we get ready to do that so that we can take that good picture. So don't please get ready for that while I'm taking this the upcoming activities. So for Lagos section, this is the first of our technical webinar series that's taking place within a few months. We have 3 more coming up. The first one will be given by Asekame Yadua of the NPDC, who is a senior petroleum engineer there. We'll be speaking on stability and stable production limit of oil production well, and that will be taking place on 21st of April and by the same time 11:30 a.m. Also, we'll be having on 4th of May and by 11:30 a.m. also a presentation on gas commercialization in a small-sized asset, a case study of a Guauma field OL38. And this will be taken by 2 facilitators from Platform Petroleum Limited, Engineer Christopher Ikeocha, who is the General Manager of Assets, and the petroleum engineer, Mrs. Kola Oyedele. Also, we'll be having on the 1st of June a presentation on the future of NLNG, past, present, and future. And our facilitators will be Malcolm Harrison, who is the owner of Harris Limited, and Phil Tudor, Director of Upstream Concept Engineering Limited. So we have very exciting technical presentations coming up. So be able to look at the registration link and take time to register. We'll also be sending out emails, and you'll also see that more on all our social media platforms, which I'll be talking about shortly. So you can connect with us more and follow us on various social media platforms. We're on LinkedIn, we're on Twitter, SP_Lagos. We're also on Instagram, SP_Lagos also. On Facebook, we are SP.Lagos. And you can also watch and replay a lot of our events on SP Lagos on YouTube. For inquiries on SP registration and your membership renewal, you can contact Obiano Kosun, Obiano or Chinelo or Agi, and their contacts and emails are displayed. If you want to know more about SP benefits, you can visit www.sp.org/en/members/benefits to learn more about what you stand to do by being a member of SP. With that, I would say thank you very much, everyone, for joining. Now, if you can show your video so we can take a snapshot and then Obion, over to you. Please help us with this session.
All right, thank you, B, and good afternoon, everyone. We've come to the point where we need to show our faces. Please kindly start your video. Let's take a few pictures. Yeah, so let's quickly start our video. You've been enabled to start your video. B, can you kindly take down the presentation so that I can have the mode? Okay. Okay, we're still waiting for, thank you. We're still waiting for others to join. Waiting for others to turn on their videos. Okay, it's popping up very quickly. Thank you. It's popping up very quickly. Thank you. Let's wait for more. Within 30 seconds, we'll click away. Thank you. Thank you. Okay, so we'll wait for 20 seconds and speed it to 15 seconds. All right, let's just 10 seconds, 5 seconds. All right, let's smile while I take the picture. Thank you. I'll just click. Thank you. Thank you. So let's do our thumbs up. When I say SP, just do thumbs up, SPE. A thumbs up. Let's just do thumbs up, SPE, and I am clicking right away. Thank you. Thank you very much from here. Thank you. B, over to you.
All right. Thank you very much, everyone. I would request for a round of applause, an E round of applause, for our speaker. And if your video is also on, you can do well to give him a round of applause and say thank you for that wonderful presentation. Thank you. Thank you very much, sir. We really enjoyed this, and this was very exciting and enlightening.
Sorry, B, have we taken the video?
Yeah, we're taking the picture. Yeah, we have. But Odion, can you quickly take another one with the second?
Yes, I think I missed
there has to be another one.
Yes.
Yes, I am. Please, the session chair, the president of SP Lagos session is on board. You know, in America, once the president is in any aircraft, that becomes Air Force One. So, section chair, you're welcome. We'll take it over again. Thank you.
Thank you.
Put on your smile, please. Okay, clicking right away. All right, thank you.
All right. Thank you very much. Thank you for joining us this afternoon. Please do well to enjoy the rest of your day, and please look out for more programs from us. We appreciate it.
Thank you very much for having me.
Thank you very much, sir. We really enjoyed this. Thank you.
My chair, I salute you. Thank you very much. Thank you, B.
All right, sir.
Have a nice afternoon.
Bye, everyone.
Have a nice day, sir.
All right, this link will go down in the next 5 seconds. Thank you. All right, thank you, everybody. Cheers.